Welcome to the Deep Dive, the place where we distill complex industry standards and research into sharp, actionable insights for you.
Glad to be here.
Today, we are undertaking what I think is a pretty critical mission. We're exploring professional software quality.
And the structured systems that are designed specifically to prevent, well, digital catastrophe.
Exactly, because if you're involved in building software, you know an error isn't just an inconvenience. It can be a potentially catastrophic financial drain.
It absolutely can. Our deep dive today is focused on dissecting the core principles that guide professional testers, quality engineers.
And for that, we're drawing from some pretty serious source material.
Yeah, extensively from the structured certification materials of the International Software Testing Qualifications Board, or ISTQB. We've also got some great research on defect prevention to complement it.
So we're essentially mapping out the anatomy of a software failure.
And learning exactly how to neutralize it, long before it ever reaches the user.
Okay, so we're starting at the foundation. ISTQB organizes its body of knowledge into, what is it, a three-tiered certification scheme.
That's right. Foundation, Advanced, and Expert. And today, we are focusing squarely on that first one, the Certified Tester Foundation Level, or CTFL.
And this foundation level is crucial, I take it.
Oh, absolutely. Its relevance spans far beyond just people with tester in their title. It's really intended for a remarkably broad audience.
Big coup.
Well, developers who need to write better code, project managers tracking schedules, business analysts defining requirements.
So everyone.
Pretty much everyone, yeah. Quality managers, too.
Yeah.
It provides that essential shared vocabulary. It covers the cognitive levels, K1, which is remembering, K2, understanding, and K3, which is applying.
And the reason everyone needs this vocabulary is because the stakes are just so high. We're talking about money here.
We are, and it's not theoretical. We have the data. According to the IBM Systems Sciences Institute, the cost curve for fixing bugs is, well, it's dramatically steep.
I've seen these numbers. The cost to fix an error found after a product release is what? 4 to 5 times as much as one you find during design.
Right. But that first figure isn't even the scary part.
Go on.
The most important metric to remember is this. The cost to fix that same bug post-release can be up to 100 times more than if you'd caught it during the maintenance phase.
100 times.
100. This knowledge isn't academic. It's a direct economic justification for investing in quality early.
Okay, let's unpack this. Let's start with a really fundamental concept. The difference between just finding a problem and actually correcting it.
A critical distinction.
Because professionally, these are handled by entirely different processes, and often different people, right?
That distinction is paramount in a professional environment. We use specific terms, testing and debugging.
Right. So testing is what?
Testing is the activity aimed at discovering those errors or bugs in the application.
And what's interesting about testing is that a lot of the time, you don't even need to know how the code works. Is that right?
Precisely. You're just testing the functionality against the requirements. It can be manual or automated, and often requires no knowledge of the source code. You're observing behavior.
In debugging.
Debugging, on the other hand, is the specialized work of the developer. It is the step-by-step process of analyzing the code structure to find the fault.
And it's aimed at correcting it.
Exactly.
Yeah.
It absolutely requires proper source code knowledge. And, it can't be fully automated. It demands human analytical skills.
Now let's look at how problems even start. The defect chain reaction. This uses 4 K2 comprehension terms that I think every team member should really understand.
Yeah, let's use that scenario from the source material. It's a great example.
Okay, so a developer is distracted by a phone ringing loudly in the next cubicle while they're trying to implement some complex calculation.
In that situation, we trace the chain backward. The root cause of the whole catastrophe is that organizational or environmental issue.
The distraction, the ringing phone.
The ringing phone, or maybe poor noise cancellation. That root cause then leads to the human component, the error.
So the error is the mistake in human judgment, the mistaken thinking, the flawed intent in the developer's mind that was caused by the distraction. They thought they typed if by 100, but they accidentally typed if by 100.
Exactly. And the result of that human error is the defect. That's the physical manifestation, the improperly coded logic that's now written into the system.
We call that the bug.
That's the bug.
And that defect, when the user or the tester interacts with the system, that eventually leads to the failure.
Right. That's the symptom you observe. Maybe the application accepts input values it shouldn't, causing a crash or incorrect processing.
So a clean chain. Root cause leads to error, creating a defect, which causes a measurable failure.
It's a very clean chain.
Hmm.
And it really highlights the tester's perspective, which is why that one analogy is so helpful.
Which one is that?
That being a software tester is like being a demolition expert in a gold mine.
The demolition expert, I like that.
Yet you aren't just looking for dust. You're looking for the biggest, most volatile risks, the biggest gold nugget to communicate immediately.
So you find the major risk, you communicate it clearly and loudly. That's the dynamite.
Right. And once the nugget is gone, the walls get shored up, the area is safe, the risk is mitigated.
It really underscores that the role isn't just clicking buttons.
Not at all.
It's about communicating and mitigating risks to the business.
That risk mitigation brings us directly to the philosophy of prevention. If we accept that analogy, then we have to adopt the philosophy that, prevention is always better than cure.
And the data here it's just staggering.
It is. When analysts trace defect costs back to their origin, they find that 64% of total defect costs originate during the requirements and design phases of a project.
64%. That means the vast majority of our financial problems were locked in before a single developer even opened their IDE.
It completely flips the script on when quality work should happen.
It forces this idea of shift-left testing.
It does. We have to find those mistakes as far left on the project timeline as possible, not just by running the code, but by reviewing the artifacts before they become code.
So how do you test something that isn't running yet? That's where the distinction between static and dynamic testing becomes essential.
Static testing is the answer there. It involves checking work products without executing the code.
So things like requirements reviews, design inspections.
Exactly. Or even examining test cases and documentation. Static testing is uniquely powerful because it can uncover things like traceability gaps.
For instance, realizing that a critical safety requirement that the user defined hasn't been adequately covered in the proposed test cases.
You got it.
And then there's the more traditional definition dynamic testing, which is actually executing the code.
Right. Running performance tests to measure, say, inadequate software response time under load.
Okay, before we move on, we have to clear something up. One of the most common misconceptions in the industry.
I think I know where you're going with this.
Quality assurance, or QA, and testing are the same thing. They're not.
They are absolutely not.
Wait, if they're separate, what does QA cover that testing doesn't? I mean, I hear those terms used interchangeably all the time.
All the time. But testing is only one part of the larger quality umbrella. It's a quality control activity focused on execution, detection, validation of the software itself.
Okay, so QA is bigger.
Much bigger. QA is a broader function focused on the proper execution of the entire process. A QA engineer is focused on preventing bugs through systemic activities.
Like what kind of activities?
Things like risk analysis, process improvement, defining standards, and ensuring legal compliance checks are baked into the design phase.
Okay, that makes sense. So a tester might report a failure in a privacy feature.
Yes.
But the QA engineer ensures the entire privacy process complies with the latest data regulations.
That's a perfect example. It's a huge shift in scope.
Right. And if a team is serious about dismantling that 64% early defect problem, they need a structured, process-focused approach.
Which brings us to the formal defect prevention process.
What's the first step in that systematic bug elimination?
It starts with data. You collect defect data from previous projects or current runs. Then you perform a structured root cause analysis, or RCA.
And how do you do that?
A vital technique here is classifying defects, understanding if they're due to environmental issues, poor communication, technical complexity, and then using a Pareto chart.
So the Pareto chart applies the 80-20 rule to bugs.
Basically, yeah. You visualize which 20% of systematic errors are responsible for 80% of the failures and all the financial pain that comes with it.
So you can target the highest frequency systematic errors that are killing the schedule and budget.
That's how you do it. This is how you systematically dismantle the root causes that are responsible for that huge 100x leap fixed cost.
And once you've identified those culprits,
teams move to tools like cause and effect diagrams, often called fishbone diagrams.
Right, and those diagrams are typically used in a group session to brainstorm all the potential factors, people, processes, tools, environment, that led to the error.
They're facilitation tools, yeah. They help you drill down and find the underlying root causes. But crucially, the final step isn't just fixing the bug.
What is it then?
It's embedding the solution, the lessons learned, as organizational baselines or checklist items for all future projects.
So you stop yourself from repeating the same expensive mistake over and over again.
Exactly.
Okay, here's where it gets really interesting for me. Once you have that foundation of mindset and prevention, how are these quality activities organized in a, high-speed, modern software development environment?
Yeah, because quality is no longer just a phase at the end.
Right.
It's not. The industry has moved emphatically toward the whole team approach.
The key advantage there being shared responsibility.
Shared responsibility. It ensures every single team member, from the product owner to the developer, is participating in quality activities.
So the developer is thinking about edge cases and unhappy paths.
Right, and the tester is involved in reviewing the very first requirement document.
And that collaboration is turbocharged by integration. What are the key benefits we see from integrating development and operations in a DevOps model?
Well, beyond the obvious benefits like faster product release and quicker time to market, the key benefit for quality is a hugely increased focus on non-functional quality characteristics.
Meaning what, exactly?
Meaning we aren't just testing if the button works anymore. We're automatically testing system performance, scalability, security, and stability, and we're doing it continuously.
Okay, let's pivot to the practical skills, the K3 application techniques that professional testers use every single day. We need to talk about black box test techniques.
Right, which rely purely on the external specification or observed behavior, regardless of how the code is implemented.
Black box testing is all about efficiency, isn't it?
It is. We use techniques to avoid testing millions of random inputs. The foundation relies on slicing up the universe of possible inputs into manageable representative chunks.
And that's where equivalence partitioning and boundary value analysis, or BVA, come in.
They're the cornerstones.
Let's run the fitness app scoring example. Say we have 5 different messages based on daily step counts. 0, 1,000 steps gets one message, 1,001, 2,000 gets another, and so on up to 6,000 plus that.
Okay, so you just defined 5 valid equivalence partitions.
Right.
So equivalence partitioning saves us time by telling us we only need to test one representative value from inside each of those 5 ranges.
Mm-hmm.
But BVA is the real secret sauce.
Because experience proves defects love to hide at the edges.
They love the edges. So for the partition 1001 to 2000, we test the boundary values themselves, 1001 and 2000, but we also test the adjacent invalid values.
1,000 and 2001.
Exactly, to ensure the system fails gracefully at those edges.
Which is much more efficient than just randomly testing, say, 1,500 steps.
Yeah.
Huge time saver.
Urge.
Another powerful black box technique is state transition testing.
Yeah, used extensively for systems that change behavior based on previous inputs or events. Think of a vending machine or a software component moving through defined phases.
Like inets, debug mode, and off.
Perfect example. When you have a state diagram like that, the key is to achieve 100% coverage of valid transitions while minimizing your test cases.
So for that example, AI to debug to off, how many tests would you need?
Well, to cover all possible valid transitions, init2 in operation, init2 debug mode to off, and so on, you'd need at least 3 distinct test cases to ensure every path from the initial state to the final state is traversed at least once.
It's about making sure the system behaves predictably as it moves through its life cycle.
That's the goal.
Okay, now let's move from black box, which ignores the code, to white box techniques, which absolutely rely on looking at the internal structure of the code for guidance. We talk about coverage here.
Yes, and the 2 primary metrics that matter are statement coverage and branch coverage.
So achieving 100% statement coverage means your tests have executed every instruction, every line of code at least once.
Correct.
So we've touched every line of code. Logically, that seems like it should be enough, right? Why do we need a second, deeper level of coverage?
That's a great question. Because merely touching a line of code doesn't mean you've tested every possible outcome of that line. Most lines of code involve a decision.
An if statement, a loop.
Right. If you only test the case where the if condition is true, you achieve 100% statement coverage. But you've completely ignored the path where the condition is false.
And that's where branch coverage comes in.
Exactly. Achieving 100% branch coverage means every decision result, both the true and false pathways, has been executed. It forces you to think about the unhappy path, not just the happy one.
So it's a measure of intellectual rigor in your testing.
It really is, and the relationship is crucial. 100% branch coverage inherently implies you've already achieved 100% statement coverage.
Because you can't test every decision outcome without executing every instruction.